Bismillahirrahmanirrahim. In this video, we'll study about transformer voltage regulation and also phasor diagram, transformer phasor diagram. So what is voltage regulation? The voltage regulation is a quantity that compares the output voltage of the transformer at no load with the output voltage at full load. So basically, let's say you want to purchase a transformer and you have been offered transformer from two companies. So one of the tests is the voltage regulation, and that means if you keep putting load on both of them, same amount of load, how much voltage is dropped at the output. So that is the basic point. And when we convert that voltage drop in terms of a percentage, then it is called voltage regulation. And so mathematically we can write that the voltage regulation is output voltage, secondary voltage Vs at no load minus Vs at full load. Now look here, the transformer, there is no load here, so this is V secondary no load, and when we connect a load, then the voltage here will call V secondary full load. So V secondary no load minus V secondary full load divided by V secondary no load and multiplied by 100%. So this is the basic definition of voltage regulation, and it can be written in some other forms as well. Now since at no load secondary voltage is equal to primary divided by A, the A is the turn ratio. So in terms of a primary voltage also we can write this, that is the V secondary no load can be written as V primary divided by the turn ratio, and these two terms remain same. Usually it is good practice to have a small voltage regulation as possible. So what does this mean is that the voltage drop or whatever is the voltage at no load should be minimally reduced when it is load is applied. So let's say it is 220. If it is 220 at no load, then with the load it should be close to 220 or to 19.5, etc. How can the voltage regulation of a transformer be determined? So let's see how we can determine this. Same question. To determine the voltage regulation of a transformer, it is necessary to understand the voltage drop within it. Now, this is the circuit referred to the secondary side, equivalent circuit, and you can see these are the excitation parameters RC. We had seen in the previous slide. It will now become RC divided by A square, because now we are referring the circuit to the secondary side. And if you don't understand this, then I'll recommend that you watch my previous video on the equivalent transformers. Okay, similarly the reactance is also divided by A square, and similarly these R equivalent and X equivalents have been calculated from this value. So this is the equivalent circuit referred to the secondary side. Now, the effect of excitation branch on the transformer voltage regulation can be ignored. Now, any drop here is minimal, so this can be ignored for the purpose of simplification. So only the series impedance need to be considered. So this is important. Okay, so if we just ignore this and we keep this, then also we'll be able to find out the output voltage or the voltage drop. Now the easiest way to determine the effect of impedance and the current phase angles on the transformer voltage regulation is to examine the phasor diagram. So one of the technique is to examine the phasor diagram or work through the phasor diagram. So let's see. Now in all the following phasor diagrams, the phasor voltage Vs is assumed to be reference voltage at 0 angle. So this is the voltage Vs, and it is taken as reference or 0 angle, and all other voltages and currents are compared to the reference voltage. So all other lines that we draw, they'll be with reference to this. So let's see. This is the circuit, and if we write the KVL equation from here, so minus Vp over A plus R equivalent into Is. Now alpha Ip is equal to Is, so the current is same Is, so we use Is plus Is Xeq and plus this voltage, secondary voltage Vs equal to 0, and from here we get Vpa is shown here. Okay, now this was the phasor diagram. A transformer phasor diagram is just a visual representation of this equation. And how is that? Let's see. So what we have here is the Vs. So this Vs. With that we add ISR equivalent. So ISR equivalent. Now the voltage and the current, they will not be in phase unless there is a purely resistive circuit. And you know, in the inductive circuit the current lags by an angle theta. So this one will be lagging by an angle theta. So we draw this, and from here the next one is Is Xeq, and you know the reactive voltage will be at 90 degree from the real voltage. So at 90 degree we draw another phasor line, and now the sum of all three, that means this plus this plus this, if you add vectorically, then this is the final voltage, which is Vp over A, Vp over A. So this is how we draw the phasor diagram. And this from here also is showing that the current is lagging the voltage by an angle theta. So same here. Okay, now you can see the phasor diagram. There are three phasor diagrams. One is for power factor lagging, other is for unity power factor, and the third one is for leading power factor. So we'll discuss all three of them. If you recall, this is the equation for the voltage regulation VR. Vpa, Vp divided by A, that is this one here, you can see, minus Vs no load and divided by Vs full load. Now let's compare the first one. It is easy to see that Vpa, that is the first term, is greater than Vs for the lagging load. So this one is greater than Vs. From the diagram you can conclude, and therefore we can say that the voltage regulation Vr will be greater than 0. Okay, now let's see the second diagram. Here also Vpa, that means this one, is greater than Vs, although not as greater as it was in this case, but still it is greater because it is the hypotenuse of a right angle triangle. So the regulation is again greater than 0, but very close to maybe unity. However, this time the voltage regulation is smaller number than it was in the case of a lagging. So the overall value will be a very small value, maybe 1% or 2%. Okay, and then we come to the third one. If the secondary current is leading, now look here, this is the current which is leading. The secondary voltage can actually be higher than the referred primary voltage. So if we have plotted this one, R equivalent Is, same as Is, and then 90 degree from here we get the reactive part, and so this is Vpa. Now if you compare this line, Vs is greater than Vp. So this is opposite of these two cases. So this will be, we call it, it's a negative voltage regulation because the answer will be in minus. And this is obviously not desired. Negative voltage regulation means the voltage increases with the load. So as you increase the load, the voltage will increase, and this is not desirable. This could be dangerous. Now let's see how we can approximate this equation. This was the original phasor diagram, and it was based on this equation. Now if you see from this, we can approximate this Vp over A as equal to this blue line. Are almost same, so that is an approximation. Now what addition has been made into this? We did up to this point is Vs, so we need to find this distance, which is shown here up to this and then up to this point. Now if you look this part and we just consider this triangle here, then this is the base of the triangle, so we can write it as equal to hypotenuse and cos of theta. So R equivalent Is and cosine of theta will give you this distance. Now this distance is slightly difficult to understand, so let's redraw the portion here. This portion I have drawn and then I have flipped it. So the theta is now here. This is the blue line that we want to find, and this blue line is same as this line. From this triangle now you can see our hypotenuse xeqis, and this is the angle theta. Therefore this is the perpendicular of the triangle, so it will be xeqis sine of theta. So we can now write this blue line also xeqis sine of theta. So now the total approximate value of Vp over A is this portion Vs, then R equivalent Is cos theta, and then x equivalent Is sine theta. Okay, then there is another term that is used for comparing two transformers, that is called the transformer efficiency. And we have learned earlier how an efficiency is defined. We know that the efficiency eta is defined as P out over P in into 100%. So in our case, P out remains same, but P in we can write it as equal to P out plus loss. From here you can see that P in is equal to P out plus loss in the line or in the system, and P out is Vs Is cos theta. So this is the general formula that we know for power, so we'll write that. And the losses are actually the copper loss and the core loss, so we'll incorporate those two, and plus output again Vs Is cos theta percentage. So this formula will be used for calculating the efficiency. Now let's see this problem given and solved in the book, example 2.5. 15 kVA 2300/230 volt transformer, that means it is a step down transformer, is to be tested to determine its excitation branch component, that is the parallel branch, and the series impedances and voltage regulations. So following data were obtained by the open circuit test and short circuit test. So these are the data that we obtained from these two tests, and now we need to find these 5 parameters. So we'll do these one by one. Now the first part of the first question is find the equivalent circuit of this transformer referred to the high voltage side. Now what is the high voltage side? This is the voltage ratio given. That means the primary is high. So high voltage side means we'll refer it to the primary side. And we have learned from the previous video the equivalent circuits. This is this circuit or the transformer referred to the primary side. So we'll use this. These are the series elements and this are the excitation elements. And this is exactly same as we did in the previous video solving example 2.2. The excitation branch values of the transformer equivalent circuit can be calculated from the open circuit test. So these two parameters are calculated from the open circuit test, and the series elements can be calculated from the short circuit test. So these two from the short circuit test. Let's see. This is the open circuit test results. Now first of all we'll calculate theta, and we know from this formula P is VI cos theta. So from there theta will be cos inverse of P open circuit divided by voltage open circuit and current open circuit. All these three parameters are given here. The power open circuit 50, voltage open circuit 2300, and the current open circuit 021. So theta angle is now 84 degrees. And the excitation admittance, that is these two, they are in parallel, so we'll write them as admittance, and we know the admittance is current divided by voltage, and we'll also take into consideration the angle, and we are putting minus sign because the current is lagging in this case, so minus sign, and IOC value and VOC value. So this is Y, and now if we transform this into polar and rectangular coordinates, so we get this answer, which is equal to 1 over RC because they are in parallel, and this is the admittance parameters, minus 1 over the J XM. And so we just equivalent or take the real part and imaginary part separately. So RC will become 1 over this real part, which is 105 kilo, and XM will become 1 over this part, which is 11 kilo. Okay, now for series elements we have to use the short circuit data as given here, and first of all we calculate the angle, which is cos inverse of the power divided by voltage and current, and we plug in the values from here. So theta short circuit is 55.4 degrees. And now from here we can find the Z equivalent, which is V short circuit divided by current short circuit with the angle, and again plugging in the values we find Z short circuit to be 4.45 plus J 6.45. Now these are the real and the imaginary parts. So from here we can find R equivalent. So R equivalent will be the real part, and the imaginary part will be X equivalent. So our circuit is now complete. We can plug in all the values. These two we found from the previous slide, and these two from this slide. So this is the complete circuit. So part 1 is answered. Now let's go to part 2. Find the equivalent circuit of this transformer referred to the low voltage side. Now for low voltage side, this is the diagram for low voltage side. They look similar, but you have to keep in mind, now this was the primary side, and this is the secondary side, or referred to the low voltage side. Now couple of difference will make the you understand. Now see the current. Here the current was I primary. Now in this case the current will be A times I primary, which is also equal to I secondary. Also the voltage here, in the earlier case it was Vp, but when it is referred to the secondary side it will be Vp over A, and similarly the other component values. So to find the equivalent circuit referred to the low voltage side, it is simply necessary to divide the impedances by A square. So you can see that the impedances have been divided by A square. So we'll just divide these impedances by A square, and the A is in this case primary over secondary is equal to 10, and the resulting values will be, now see, we just dividing, if we divide this one 105 by A square, that is 100, so we get 1050 ohms. Similarly, dividing the other, we get the new value. So this is the equivalent transfer circuit referred to the secondary side. Okay, now this part may be slightly difficult, so pay attention. What we have to do here is we have to calculate the voltage regulation at these power factors. This is the circuit referred to the secondary side. We'll use this circuit, and the property of the transformer is given. It is power is 15 kVA, and the primary side is 2300 volt, and the secondary side is 230 volt. Now this formula we have learned for the voltage regulation, so we need to find Vp over A, and we need to find Vs full load, which is actually 230 volts. So this is known, Vs full load. All we need to find is Vp over A, and this we had seen that we can find this from this equation here. Vs we already know, as I told you, it is 230 volt. So, and R equivalent and X equivalent are given in the diagram. We had calculated this earlier. So if you know Is, then we can find Vp over A, and then we can find the voltage regulation. So let's see how we can find Is. Okay, from the power formula, the current rated is power rated divided by voltage rated. So power rated is 15 kVA, voltage rated at the secondary is 230. Therefore, current rated is 625.2 ampere. And we need to find the angle as well. So for 0.8 power factor lagging, the angle will be minus 36.9, lag minus sign because it is lagging, and we got this from cos inverse of the power factor, that is 0.8. So cos inverse of 0.8 is 36.9, and we put the minus sign. So we have now find the current. So putting in now the values of in this equation, Vs, then R equivalent into Is. So R equivalent is this value here, multiply by this current. Similarly, X equivalent multiply by the current, and solving we get the final answer to be 234.85 angle 0.40. we could have skipped this step, but this will help us in plotting, and that is why this is a necessary step. And now that VPA is known, so we will use this formula to calculate the voltage regulation. So VP over A is this value, 230 divided by 230. So voltage regulation is 2.1%. And if you want to plot, this is the plot. 230 volt is the reference. Current is at minus 36.9 degree. So this is the current. So here we draw it. I into R equivalent, that is 2.9, this value here. We are plotting it here. And then at 90 degree, we plot this value, 421 at angle 53 from here. So 53, if you add this, it will be 90 degree. So anyway, this is done, and now if you add, you can get the VPA. So this is the phasor plot, and we have found the first part, that is for 0.8 lagging, the voltage regulation is 2.1%. Now let's see for the other two. Same technique. At 1, the current will have a 0 degree angle. So 230 and this multiply by 62.51, the real part, R equivalent, and then the imaginary part multiplied by the angle. Again, we get 3 terms. It will help us plotting. So this is the final value, and we can now use the voltage regulation equation. And so in this case, you can see that the regulation is 1.28%. So in the case when PF is 1, the regulation has reduced from 2 point something in the previous case. It has now reduced to 1.28. And here also you can plot. This is the VS, and then along with that is the real part, which is this part. And then we have the imaginary part, which is this part at 90 degree, and the summation is the VP over A. Now let's go to the third part, where power factor is leading. So the current will be as shown here. Now the current is, you can see it is positive, showing leading, and again following similar technique. Now we find VP over A to be this value given, and now we can calculate the voltage regulation. Plugging in the values, you can see that the regulation is now negative. This generally happens when the load is capacitive, and as we have mentioned that this should be avoided, not desirable. Okay, plot same technique. Now the angle has gone positive, therefore IR equivalent will also be positive. So this is the value. From here 90 degree we get the imaginary part, and so the sum total is VPA, VP over A, this one. So this completes the part C, and now part D. Plot the voltage regulations as load is increased from no load to full load. So if you can see in this diagram, no load, that is 0, and then we're increasing the load. The best way to plot the voltage regulations as a function of load is to repeat calculations in part C for many different loads using MATLAB. We will not go into that. In your book, the MATLAB program is given, so you can type and get the answer. But the only thing you can see from here is the 3 performance characteristics. They are almost linear. For power factor lagging, the voltage regulation is higher. The power factor 1, it is just constant slope, and for power factor leading, it is going towards the negative side. And finally, we need to calculate the efficiency of the transformer at power factor 0.8 lagging. This is the formula for efficiency. So all we need to find out is the copper loss and the core loss. We already know these values, so we'll plug in. Now the copper loss is due to the series resistance. So I square R or IS square R. We know IS 65.2 square and R, so it will be 189 watt. And similarly, the power loss due to the core loss is V over R, V square over R, and VPA we already know the value, divided by RC. This is RC 1050. So the core loss is 52.5 watt. And now the output power, VS IS cos, again we know VS, we know IS, and we know the angle, so cos theta, it will be 12,000 watt. And now plugging in all the values, we find the transformer efficiency to be 98.03%. So I hope you have understood how you can solve this type of a difficult problem by following the steps. Thank you.